Hello everyone, I am Ram Saravanan Kumaran and register number 951, and today I am going to give the introduction for our group presentation. We have picked the topic of minimum spanning trees for our group video presentation. So, a minimum spanning tree by definition is a subset of all the edges of a weighted and undirected graph in data structures. It basically connects all the vertices of a graph together with minimum possible edge weight. So, I'll give you a brief introduction about the terms which are going to be used in the presentation so you can understand better. A graph is a collection of vertices which are basically nodes and edges which are connection between those nodes. A weighted graph is and each edge will have a numerical value which represents cost or distance or other any metrics which are supposed to be represented using the graph. A spanning tree, a normal spanning tree, is a subset of a graph which includes all the vertices and it's in a tree. And a minimum spanning tree is among all the spanning trees, it has the least possible value of sum of edge weights. To find a minimum spanning tree, there is two methods. The first one being Kruskal's algorithm and the second one being Prim's algorithm. Both of these will be explained by my teammates. And a basic application example of usage of minimum spanning trees is network design and telecommunication and computer networks.
Hello everyone, I am Kaushik. I am here to explain Prim's algorithm and Kruskal's algorithm, which are two powerful tools for finding minimum spanning tree in a network, which helps connect all nodes with minimal total edge weight. Prim's algorithm begins with a single node, then progressively expands the tree by adding the smallest edge that connects an included node to an excluded one. This process ensures each added edge is of minimal weight, gradually growing the MST without backtracking or cycles. Prim's approach is particularly efficient in dense graphs, where there are many possible connections to evaluate, since it builds the MST by continuously expanding from existing nodes. It naturally adapts to the larger networks by focusing only on the smallest edge at each step, keeping the cost to a minimum. Kruskal's algorithm, by contrast, starts with all edges sorted in ascending order of weight and approaches the problem from the edge side. Using a union-find data structure, it adds edges one at a time, provided they connect previously unconnected parts of the graph and don't form cycles. This technique keeps the overall tree minimal and cycle-free, especially effective in sparse graphs where there are few edges to evaluate. Kruskal's method is efficient in situations where edge sorting provides a natural way to minimize the MST, and the union find structure ensures connected components merge smoothly. In 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 conclusion of these topics, both algorithms are optimized for connecting nodes efficiently, with Prince excelling in dense networks by expanding node by node, and Kruskal's shining in the sparse ones by focusing on edges first. Together, they provide versatile solutions for MST problems in diverse graph structures, allowing us to find cost-effective cycle-free connections for any network.
My name is N. Srinivasan and I am going to speak on the topic analyzing the time complexity of MST algorithm. So, when analyzing the time complexity of minimum spanning tree MST algorithm, we primarily look at two popular ones. So, it's Kruskal's algorithm and Prim's algorithm. Both use a greedy approach to minimize the total weight of edges in the tree. Here's the breakdown of each algorithm's time complexity. So it's Kruskal algorithm. The Kruskal algorithm's process is to sort all edges in non-decreasing order of their weights and then pick the small edge and doesn't form a cycle. So using a union field data structure to check the cycles. So now let us see its time complexity. Sorting edges O E log E, where E is the number of edges. Union find operation with path compression and union by rank OE dot AV. So here A, that is alpha, is inverse function a very slow growing function, almost a constant. So now let us look on Prim's algorithm. So Prim's algorithm's process starts with a single vertex and grows the MST by adding the minimum weight edge connected to its current MST. It's typically implemented using a priority queue, min heap, to efficiently get the next minimum edge. So now let us look on its time complexity. Using a list and a minimum heap, building a minimum heap is O E plus V log V, where V is the number of vertices. Updating and extracting elements from the heap is O E log V. So now let us see the comparison between the Kruskal's and Prim's algorithm for finding minimum spanning tree. First, let us look at the approach. The approach of Kruskal's algorithm works on sorting all edges and repeatedly adding the small edge, and it doesn't form a cycle, and focusing on edges and operates on the entire graph edge list. So now let us look on Prim's algorithm. Starts from a single node and grows MST by adding a minimum weight edge connected to the current MST, and it's focused on vertices and operates incrementally by expanding the current MST. So now let us look on data structures used in both the algorithm. First, Kruskal's algorithm. So it's primarily used on union fine data structure to detect the cycle efficiently. So now Prim's algorithm often use minimum heap to select the small edge connecting to the MST efficiently. So now let us look on the time complexity of Kruskal's and Prim's algorithm. So time complexity is O log E log, or equivalently O E log V, since E is greater than V minus 1 in connected graphs, dominated by sorting the edges using the union field operation. Now let us look on the Prim's algorithm. So complexity is O E log V with a minimum heap implementation, generally more efficient in dense graph where E is much larger than V, and it depends more on vertices than edges. Thank you.
Hi, this is Varshan, register number 975, going to talk on the topic of telecommunication networks. MSTs helps design network like cable, telecommunication or electrical networks with the minimum cost by connecting all the nodes with least total length of cable or wires. Computer networks in laying out a network of computers or data centers where MSTs can help minimize the cost of wiring while ensuring that each computer is connected together. Transportation and road systems, where MSTs aid in playing road systems or rail networks to connect cities locations using minimum road length. This can be useful in designing infrastructure where construction costs are high and minimizing the total travel destination in essential. Third, circuit designing. Print circuit board PCBs where layout of MSTs are helpful in connecting different circuits components with the minimum amount of wiring and materials. This minimizes resistance and manufacturing cost. The key takeaway on minimum spanning tree. The main goal of minimum spanning tree is to connect all nodes in a graph with the minimum possible total edge weights, ensuring no recycle and fully connectivity. Where a graph can have multiple MSTs in multiple edges having the same weight, but all MSTs will have the same weight. Cost effective connecting are special value in real world situation where minimizing the cost of usage is important, such in network routing, transportation and supply of chain. These are key takeaway of minimum spanning tree. Thank you.